Hey, hi guys, this is Ajay Sasodia, and in continuation of small AFA video series, I'm back with another small video, the video number 4. And today's question is, I hope it's visible to you guys. Very fine mesh leads to a higher accuracy. Then why we go for lower order mesh, right? Mesh size. I mean, the question is like, if you know, like, if a fine mesh is better, then why should you are going with the coarse mesh, right? Directly you should jump to the fine mesh. Or another word you can see here, if we increase the number of calculations points, nodes and elements. Calculation points means nodes and elements. Okay, is the accuracies increase or decrease? So this is very important questions. I'll repeat it once again here. The second question here is because the answer is there in the question itself. If I increase the calculation point, whether the accuracy will increase or decrease. So the answer is yes. If you increase the number of calculation point, your accuracy will increase. Okay. If your accuracy is increased, then why the coarse mesh is there? Software should have only fine mesh, right? This is the question is coming in your mind, correct? There is a reason. There is a reason behind of why these options are available and when you should use coarse mesh and when you should fine mesh. There is a reason. Okay, we'll go through in the detail here. So I have another picture here. Before that, I'll put one very small conceptual thing here. Suppose if you have a circle and you're supposed to fit the circle with 3 lines, okay, let's say triangle, right? Let's say triangle, and find the area of that circle and compare it with 4, 6, 8, 16, 32 and 64 lines. So look at here look at here. So don't mind it, I just roughly, with freehand I draw it here, right? So look at the circle here. This is the one circle, right? And here there's a triangle, like 3 lines, 4 lines, okay, and you can see here it's 6 lines, 8 lines, okay. So up to here I have plotted. So you can easily see this shaded area, right? This is the area of error, okay. So if you increase the number of lines, okay, from 3 to 4 to 6 to 8, so you can look at this, right? So your area is decreasing, right? So your error margin is reduced, right? Understood? So the number of straight lines are basically equivalent to the number of elements in finite element analysis. So obviously, if you capture more lines, right, more area, your accuracy will increase. Okay. So assume that exact area of the circle, pi r square, exact area of the circle is 100, but you are getting area with using 3 line, let's say 41, or okay, and let's say for 4 line 64 and so on, right? So with the 3 line you are getting 41 and with 4 line 64 and so, and actual area is 100. Okay, so whether it is right or wrong, obviously it's not right. There is a drastical difference. So the answer 41 or 64 is not acceptable. That's not acceptable. Why it is not acceptable? It is there is a big difference from 100 to 41 and 64. Yes, up to 80 to 90, it is considerable depending on how much time you have spent, right? Depending on the design phase you are involved in it. For example, if you are involving in the conceptual level design simulation, then you can go with a coarse mesh and identify the hot spots where the hot spots are coming, and later on you can go for a fine mesh at that particular area and you can simulate the problem. Okay, so you can go with the combination of both area. I mean combination of both type of meshings. Linear means quadratic. Okay, fine means higher order meshing also. Getting it? So the coarse and higher order mixing and the combination of both type of meshing can be performed in one single problem to get up accurate result, to make a stability. Okay. Now question is where to put coarse mesh and where to put fine mesh. Okay. For example, I'll give you one very simple the example here. So we did one project for our Australian client, and the Australian client basically he needs that results, the simulation results, within 2 days. and there were number of designs of the changes. Okay, so we have to solve within a 2 days with detailed report also. Okay, have to deliver the report also, so it take obviously time. So the time given for the project was very small. So that is the basically answer. Okay, that this is the answer whether we should go with fine mesh or the coarse mesh. So this is the one reason that if the customer is not providing you in a proper time, he needs results quickly, fast. Maybe depending on, he already knows about it. Maybe depending on he is involved in the first phase of the design, it doesn't care about that for more fine mesh. Better is to obtain the result from the coarse mesh and look at the the hotspots, and later on you can submodel it, or maybe you can go with a fine mesh like a critical areas like holes, like bearing areas, like fillets, like corners, like where you're applying the loads, you are fixing at the critical points. So you can go with that combination also, and you can make it a coarse mesh to the flat surface, the surface and the area which is not much contributing in force transmissions, right? So this is how you can combine the coarse and fine mesh. So the answer is solution time. And also obviously if you go for fine mesh, your degree of freedom will increase, right? You'll see large degree of freedoms here, right? So I'll show you one graph here. Look at the graph, right? So in this graph, if see here, this graph, the number of line versus the area. Okay, so solution time drastically increase, and basically it is directly proportional to the degree of freedom. Okay, so the n equals to 1 to 4. Okay, depending on what type of analysis you are solving, whether it's implicit, explicit, linear, non-linear, dynamic, what type of analysis you are solving, the time will increase, and that will varies. Okay, and also the size of your mesh, also the model size, also the computational power and the hardware power of your workstation on the computer on which you are solving. These all are the important things, and the graphic cards, memories, lot of factors involved in getting the results. Okay, and then again it is all basically comes under the solution time. Okay, so how to decide element size again, because because this is all are increasing, right? Look at this. Can you see the graph here, right? So if you are having three lines, you will obtaining 41 area at 464. So as you increasing the number of line, you are coming close to the exact solution of 100, right? But again you have to increase the element size, right? So what you can do, as I said earlier, like you can make a combination of element size, fine and coarse, depending on the critical areas, depending on the hotspots, and depending on the area where basically the chances of getting more stresses will come. Okay, also if you are considering frictional contacts, right? So master at silly surface, try to keep it a good balance of fine mesh, or maybe the similar kind of mesh order. Okay, now so as we have assumed that the analytical methods giving you the 100% accurate results, right? Let's say 100. Okay, but what happening here is 100 times 100, but you are getting 100 results. But at how much the time it took? It took 1 month. Okay, if you calculate, it took 1 month. I'm not talking about this simple pi r square and you are feeding it, right? In an analytical method, when you go to the numerical method, in 1 day you will achieve 85 to 90, or maybe even you can increase it, right? That much area in numerical method. Okay, so in industry, it is very important in some cases. I'm not saying in all cases, but in some cases, in the most of the cases, forget about the some cases, in the most of the cases in industry, it is very important to achieve results quickly. So which one is better? Obviously, in analytical method, you are getting 100% results, 100 as an area, but it took 1 month, while in the numerical method, in 1 day, you are getting 90. Obviously, it is right to go with this, right? But I'm not saying this is again accurate, but you have to be think in lot of factors depending on what type of at what stage basically you are solving the simulation problem. It is, if it is at final stage, then go with the fine mesh, go with the second order, or maybe go with the chord, or maybe brick meshing and all the options whatever available with you. But it is not always to go with that fine mesh. So I'll give you a few tips here. What we do generally, whenever you have any project, we always go with first linear mesh. Okay, always with first linear mesh. After doing the linear meshing, applying loads and beats and everything, so we'll get a results. From the results, we will understood the hotspot region. Then what you'll do, we'll modify that local area where we are getting some local concentrated stresses, localized stresses, okay, and some other spots and some other highlighted area which we supposed to get some more stresses, right? And then we'll locally modify it and we'll simulate again, and we'll achieve a very good quality of results in a very short period of time, and also will satisfy our customer, because in industry the customer don't want to wait it, right? But of course, if you convince your customer and if it is involve a very detailed simulation, then you go with the higher order elements. And if you are going with triangular elements, we always recommend it to go with R trias, okay, instead of going only with triangular elements. And it is always obviously better to go with brick element, chord elements, hexadominant element, but it is not easy to mesh it in a complicated and industrial big problems. So we'll go with usually with the R trias meshing scenario. So analytical method is basically known as a scientific way of solving any problem, whereas numerical method is the engineering way of solving any problems. Okay, I hope guys I've answered these questions, and I hope you people have got something from this video. Thank you so much. I'll see you in the next video soon. Bye. Take care.